So we're going to take a look at density curves. What those look like. It just pops up. There we go. So right off the bat, if we're talking about some kind of density curve, the area under any density curve is 1. And the reason is we're going to start to use these curves to solve problems associated with proportions or probabilities. So for example, we take a look at a problem like this, and we can see that we have this triangle associated with a humor level during class, if you will. Um, so right away we can see the area associated with this curve is 1/2 base times height, which we should recognize as 1/2 times 0.5 times 4 is 1. So here's what I'm talking about with probability, or proportions. What proportion of observations fall between 2 and 4 minutes? Or in other words, what's the probability that we're between 2 and 4 minutes? So for us, what we're looking at there is essentially you take this particular area, we're trying to figure out the area of that particular triangle. Right? And although that's half the time, that's not half of the area of the triangle. It actually ends up being 1/4. And we could do that with that area equals 1/2 base times height. Right? So there's the 1/2. The base of that is 2 minutes, and then the height is 0.25. Right? So the overall height of the triangle is 0.5. So the height of the smaller triangle we just did, those would cancel. We'd be left with 0.25. Right? We could also, what's the proportion of observation was in the first 2 minutes? So in other words, the probability that X, some observed phenomenon, in this particular case, our observation of humor, was less than 2. Well, thinking about this, if the whole area under the curve is 1, then all of a sudden, if we go, well, we know from 2 to 4 is 0.25, that leaves the rest of it is 0.75, and that's actually called the complement rule. Right? So how does that play out for us in the statistical world? So let's say we're looking at this particular histogram of 50 students. So what proportion of students scored below a 70? So one way we could do that, we could total up. There's 2 observations, there's 5 observations, and there's 6 observations, and then we basically would take that total, right, from 70 and below, and we'd end up realizing there's 14 total out of 50, or 28%. Same thing if we did 75 to 100. So in other words, we're going to start there and work our way up. Well, again, if we count the height of each bar, we'd end up with 25 out of 50. Right? Now, these grades, as we would add more students, like this is a pretty common shape that a lot of us are familiar with in terms of like a bell curve. But some, some variability in the curve. But if we added more and more students, actually this thing's going to look more and more like a bell curve. That's an important phenomenon as we keep moving. So again, keep in mind the area under the entire curve is 1. And so what we can do is we can find the area of a certain interval to represent a proportion of events, kind of like we did here, right? If you imagine, here's a curve. Draw a curve over those. If I were to shade, if I said the whole area under my bell curve is 1, right, if we look back at that very first example, if I were to shade everything from the score of 70 and below, that's probably really, really close to about a 28%, or maybe about a third, somewhere between a third and a fourth of the curve that I'm shading in right now. Same thing if you look very, very closely. Um, if you from 75% on, I'll switch the colors. Or 75, score 75. Well, that's pretty much right in the middle of the curve. So, and sure enough, we called that a 50 before. So that's kind of the idea what's going on. So we're going to take these histograms that are kind of what somebody might also call normally distributed, and we're going to put that bell curve so we get to we start to get a shape of what's going on. So there's what we did using our histogram. 14 out of the 50 were 28%. And there actually is a way to calculate that area under the curve, which in this particular case is about 35%. Where does the difference come from? Well, if you look, there's some gaps underneath the curve that aren't really accounted for, and that's where that extra probably 7% is going to come from. We'll talk about how to get that in just a little bit. Right? Between the 75 and 100, we said counting it was 25 out of 50, or 50%. But if you did the shading, it's actually 43. Well, here's an example where you can see all these portions of the histogram are actually, more of the portions are actually above the line. So counting up the pieces of the histogram, that's one way to get the proportions, but as we get bigger and bigger groups, it's going to be hard to keep counting up boxes, right? If we had 1,000 people, we don't really want to take the time to count all those individual bars. So what we're going to end up doing is we're going to use some of these ideas about certain samples to start making calls about the overall population. So let's say that we have the actual data. We're taking the mean and the standard deviation, and what we want to do is we want to go ahead and make some kind of observation about the population as a whole. So this is all just notation. So the mu and the sigma, the Greek letters, these Greek letters, those are standing for something that's telling you about the population. And that's something that's really hard to get your hands on if you really think about collecting data. It's very easy to get sample data, right? We can sample 100 people here at Gibbons and figure out the average height and standard deviation of that group. But to get the whole population at Gibbons and to get the average height of everybody at Gibbons, that'd be a little bit tougher to do. So that's kind of what we're going to end up taking these sample distributions and trying to make calls about a population, if you will. So this normal distribution, or that bell curve, right? We threw that term out there just a minute ago. So that bell curve, it has what we're going to start calling a normal distribution, if you will. And a lot of things that you interact with on a daily basis, test scores, people's heights, distribution of soda cans, right? How much soda is actually in a soda can, because it varies from can to can, the filling mechanics. As we could describe a normal distribution, it's symmetric, it's single-peaked, and it's mound-shaped. Just a quick harken back to the SOX days. And so what we're going to do with the normal curve, there are an infinite number of different curves that can be constructed, right? For every different normal situation, like the scores on a science test, the scores on a math test, the height of students at Gibbons, the height of students at Leesville Road High School, the height of students at Apex High School. So there's just curves after curves after curves. But what we can do is we can start to define these things based on the mean and the standard deviation that each individual curve talks about. The one that we're going to use right now is the normal curve with a mean of 0, so it's going to be balanced at 0 with a standard deviation of 1, right? And the way this is going to play out for us really effectively, and you're going to get very, very familiar with this and used to it, is what's called the empirical rule. Some would call it the 68, 95, 99.7 rule. As I'm trying to kind of write on this, sorry that the handwriting is terrible. The touch screen's not working for me for some reason today. Some people call the empirical rule that right there. So in general, it's telling you kind of how much area is underneath this particular normal curve when we're talking about a standard deviation away, 2 standard deviations, 3 standard deviations. So what we can really see is that most of the data all of a sudden is going to be within 2 standard deviations of the mean. We'll let this play out here in just a second. So again, 68. So we split that in half, we get 34% on both sides there. And then as you can see, like as the curve drops, we're losing area, right? It's actually the same, the gap is the same, but as the curve drops, we obviously lose area under the curve. And then to get that 99.7, right, we went from 95% up to 99.7, so we got another 4.7% that we have to split between the 2 different little tails right here. So each one of those is actually only 2.35%. And then the very outside, if there's 99.7, that tells us there's another 0.3%, but that's not accounted for, so that's where the 0.15 way out here beyond the tail goes. If we think about percentiles, you guys are probably really familiar with percentiles. So the 50th percentile would put you right in the middle of the curve. The 0th percentile, not really where you want to be. As you can see, what these are going to do, they're going to sum up. So 0.15 plus 2.35 is 2.5%. That's where that 2.5, we add the 13.5% to it. 13.5 plus 2.5 is 16. We add the next chunk, 34% plus 16 is 50. And you're just going to keep going up. So add another 34% to 50, that puts you at the 84th percent. Add another 13.5, and really what it's doing, percentiles, just like the RCFs and ogives, it's accumulating. Add another 13.5 to the 84, 97.5, so on and so forth. So let's say that we have this distribution of Army helmets. and the average height, the average circumference of the Army helmets, the average head size in the Army is 22.8 inches, and the standard deviation, I'll use that term sigma, is 1.1 inch. So if we go ahead and we say, okay, this normal curve is going to be centered at 22.8, and then I'm just going to add and subtract 1.1 inch as we go out each standard deviation. How does this play out for us? So if we think about this, what percentage of helmets are between 21.7 and 23.9 inches? So 21.7 is here, 23.9 is here. Well, that's within one standard deviation. And using my empirical rule, which we talked about earlier, I can slide all the way back. You see that that's 68%. So what percentage are between 21.7 and 23.9 in our particular case? That'd be 68%. All right, between 21.7 and 25. 21.7 and 25. So we got the 68% plus another, if you remember, that's 13.5% from before, right? So we do 68 plus 13.5 puts me at 81.5%. Above 26.1 inches. So here's 26.1. What's everything from here up? So if we recall, that's actually going to be associated with 0.15%. Very, very few people would have a head this big. So 0.15%, not 15%, 0.15%. Very, very few people would have a head more than 26.1 inches. And then between 23 and 24 inches, well, those actually aren't here, but we can use our empirical rule to get a good guess. So there's 24. 23 is just above the mean, so it's we're very, very close to this middle chunk right here. And that's half of our 68%, which would put us at 34%. And because I'm not right on one of my standard deviations, I'm going to say about 34%. Now we could also use that curve to do percentiles. So what percentile is associated with 22.8 inches, right? So I'll switch colors, just keep using that same curve. 22.8 inches is right there in the middle. That puts you a halfway point, so that would be the 50th percentile. Okay, and this is just using areas under the curve, everything that's below it, right, as it's accumulated, right? I would shade half of the curve right here. All right, 19.5 inches. 19.5 puts me way down here. That'd be a really, really small head. And we could see, again, that tail probability is 0.15. So that would put you in the 0.15% of people are below you there. So that actually puts you in the 0.0015 percentile. It's pretty low. And then 25 inches, again, we don't have exactly, oh yeah, we do have 25%. It's right here. So in other words, what area is all of this? Right? What area is all of that? And that would be, you got, the way that I would approach it, I know that up to here is 50, and then we know, so it's halfway point is 50, and then we got another 34% up to 23.9, and then remember there's another 13.5%. So if we add all those together, 50 plus 34 plus 13.5, we get, if we look at the previous slide, we get that number right there, 97.5. So to be 2 standard deviations above puts you in the 97.5 percentile.